And this is the solution that was prepared earlier on for question 19. So let's proceed to question 20. Question 20 says that burgers are sold plain or with any selection of the available toppings. Burgers with different sizes um, burgers with a different selection toppings, including with none, are considered different types. Okay, so you've got Rocco Burger has 192 more types of burgers than Burger Bry, but uses only two more toppings than Burger Bry. How many types of burgers does Burger Bry have? Okay, let's try to understand this question. What it is saying is that there are two types of burgers. One we'll call Rocco Burger, and another one is Burger Bry. And there are several types of toppings that you can put onto this burger. So you have maybe cheese or cheese and tomato or whatever. Um, so it's quite possible you could have maybe 3 or 4 toppings, ketchup and mustard and whatnot. So, but we don't know how many toppings there are. So it says here that different topics are considered different types. So you could have no topping, or maybe one topping, or 2 toppings, or 3 toppings, or whatever, right? Um, so how many different types of toppings burgers can you have? They say different selections of toppings are considered different types. All right, so if you have no toppings, that gives you, okay, all right, I think the way to do this is they ask you, um, we don't know how many toppings there are. Okay, suppose there are n toppings. Suppose Rocco Burger, or let's take the other one, Burger Bry. Suppose it has n toppings. And Burger Bry, but uses only 2 more toppings than Burger Bry. So then R has got n plus 2 toppings. All right, now we like to know how many different types of burgers that you've got. Okay, we can take a simple situation like suppose there were 3 toppings, maybe cheese and uh, ketchup and chicken burger. Right. Now a person can say, okay, I'm going to have nothing. So that's one. Otherwise, a person can say, I'm going to have cheese, ketchup, and cheese and ketchup. Another person can say, I can have what is this? Chicken. I'll make a chicken. Another person can say, I'll have uh, what is it? This is cheese. It's ketchup. So another person can have cheese and chicken and ketchup. Another person can have cheese and chicken, like that. So there are various different possibilities, and if you work out all of them, or they can have only one. They can say, "I'll only have cheese. I'll only have ketchup. Only have chicken." Or otherwise, you could have all three. You can say, "I can have cheese, uh, ketchup, and chicken." So you can see you got quite a few. If you count this one here, you got eight with three toppings. There are eight types. Right. Actually, if you work out for four toppings, you'll have 16 types. See? And in general, if you have n toppings, you have, there's 8 is 2 cubed, 16 is 2 to the power of 4. With four toppings, you got 2 to the power of 4 types of burgers. All right. Sorry, I'm squeezing everything here. I wonder if I can make a. Yeah, okay, I can do that. All right, so let me just analyze this thing properly now. Okay, so I'm suggesting that if you've got n toppings, you've got 2 to the n types of burgers. Now, you can actually argue this thing out as follows. Suppose we say we got n toppings, right? And we want to find out how many types of burgers do you have. So I'm going to put boxes here like this, something like that. Now, either you have a topping or not. Right. This could be included, could be yes or no. These are the different toppings. Here too, you got yes or no, yes or no, and so on. These are the different toppings that you have. So each topping, you can choose them in two different possibilities, either yes or no, right? So if there are n toppings, each one, there are two choices. So therefore, the total number of choices, types, number of types, and the n is 2 to the power of n. Right. So if you go back to our problem, I said that one of them has got n toppings and the other has got n plus 2 toppings. And the problem says that there are 192 more in one than the other. So in fact, you have 2 to the power of n plus 2 is the number of types of the one which has got more toppings, and you got 2 to the power of n types for the one which has got 2 less toppings. And they say this is more than that by 192. Right. So, so you got an equation, but this is an exponential equation. You don't have the unknown is in the exponent. This is 4 times 2 to the power of n, 2 squared times 2 to the power of n. And now you can take out 2 to the power of n as a common factor. 4 minus 1 is 3. 192 divided by 3 is 64. So n is equal to 6. See? So there are 6 possible toppings that you have in the original one. and the one which has got extra has got 8 toppings. So they say, how many types of burgers does Burger Bry have? Now, Burger Bry was a smaller one. So the answer is, so the answer is the following: number of types of Burger Bry is 2 to the power of n, and we saw n is 6, 64. The one extra has got the Rocco Burger will have 64 plus 192, which is 256. That is 2 to the power of 8. Okay, so that's the answer to that question. All right, okay, there it is. I also worked it out probably exactly the same way. I got the same answer. Let's go to question 21. Question 21 says you've got a square ABCD. You can see it. And point G lies on AD. There you can see it's there. And there's G. Uh, the line segment GE extended. So you got E is the midpoint. You got AE equals BE is equal to 3. So this is extended to meet that. Okay, the diagram speaks for itself. All right. But you also have that angle EGC is equal to angle BCG. So let's just record that. I don't know how to take this thing out. Okay. So you got angle EGC, this angle here, is equal to BCG. So in other words, this triangle here is isosceles. Okay. So now the question is, what is the area of the shaded region? All right, let's have a look at this problem. So we need to find the area of the shaded region. Now, you see, if this is 3, 3, and these are vertically opposite angles, otherwise this is 90 degrees. So you can see that these two triangles are actually congruent, right? Which means that these two are equal here. And like that, likewise, these are equal. They're congruent. All right, so the question is now, what is the area of this? Well, the side of the square is 6, as you can see. So all the sides are 6. So let's call this 6. And we don't need to find the area of this. Let's call this x. Because if I know x, then I should be able to calculate. Then I know the area of that, and I might be able to calculate the area of the whole thing and subtract the two to get that. So that looks like a good starting point. Anyway, so you got 6 plus x. Now remember, this part, this is also equal to x, right? So, which means that this thing here, the whole thing is 6. So this part here is 6 minus x. Okay. Now, this is 6 plus x, and this triangle is isosceles, we notice this. So this is also 6 plus x. So each one of them will be half of that. So let me do this. Let's call this 2x. And then this will be 2x. So that way I can say half of that, half of 6 plus 2x is 3 plus x. I don't have any fractions. So you get 3 plus x here and you get 3 plus x here. I'm just building up this whole thing so that we need to calculate the area of the shaded region. Okay. And so what do we have? We need to calculate x. Now in this triangle here, I've got a right angle triangle with 3, 2x, and 3 plus x. So you can use Pythagoras to get 3 plus x all squared is equal to 3 squared plus 2x all squared using Pythagoras. So you got 4x squared here. Just do this. This is 9 plus 6x plus x squared equals 9 plus 4x squared. And the 9 cancels. And you have 3x squared minus 6x equals 0. When you take this to the other side, 4x squared minus x squared is 3x squared. And that gives you that x is 0 or 2. Now, x equals 0. Yeah, obviously, you can't have 0 here because so 0 can be disregarded. Otherwise, this length here is 0. And that contradicts what we've got. So x is actually equal to 2, which means I can replace this 2x here, make that 4. And this will also be 4. X is 2 now. So this is 4. And therefore this will be 2. So I think we are getting there because we've got the dimensions of this this whole thing. Okay, so this will be 5, 3 plus 2. So you got this triangle, its area will be, you got 4 and 3. So this area is 6, half base times height. 4 times 3 is 12 divided by 2. The area of this full triangle, okay, so if that is 6, this is also 6 then. Because these two triangles are congruent. Oh, yes. This is 2 and this is 6 here. All right? Because the opposite sides of a square. And this is 2. So the half base times height will be 6 here again. So now we've got we've got everything in the square here. The area of the square is equal to, well, it's 6 squared, which is 36. But that's also equal to, the area of the square is equal to 6 plus 6, which is 12. 12 plus the shaded area. So that gives you the shaded area. It's 36 minus 12, which is 24. All right, so the key point here was to recognize these two triangles are congruent, give a name to some unknown thing, and try to calculate that unknown. I chose this particular thing as x because I thought I can find the area of the triangle, the large triangle, minus the area of the small triangle will give you the area of this. But then we saw that if you call this x, then we needed to get half of 6 plus x, which is not very nice. So if I called it 2x, half of that would be 3 plus x. That helped me to work this thing out quite accurately. All right, without too much of fuss and bother. So let's just clear the drawings and choose the next slide. Well, let's just check to see what we've got. Oh, right, okay. It's virtually, it's exactly the same. So you see that I've got 24 there. Okay, so let's get to the next question. Question 22. Very often in these advanced competitions, questions are given like this of sequences, because you do arithmetic sequences, you do geometric sequences, but there are other types of sequences, and this one here is an example of such a case. And you have to deal with different types of problems involving sequences. So here, the term, normally you use T, N for the nth term, but sometimes people use other symbols, like this is the kth term. So consider the sequence defined by, so this is the kth term. So for instance, when k equals 1, it's 1 over 2. When k equals 2, you got 2 squared plus 2 is 4 plus 2 is 6, 1 over 6. So you got k into k plus 1 at the bottom. So you got 1 over, this is 2 times 3, and 3 times 4, 4 times 5, and so on, 5 times 6. So this is your sequence, all right? And you're adding all these terms. If you add all these terms right up to some term, n minus 1th term, you're going to get 1 over 29. Oh, but wait a minute, you're only adding a piece of this. From one point, AM, it starts from maybe 1 over 12 plus 1 over 20 plus 1 over 30. And they give you what this partial, what we call a partial sum, right? They give you that answer is 1 over 29. And the question is, how do you calculate m plus n? That is a problem. So this looks like quite a challenging problem. But I want you to notice, you see this k squared plus k is quite a popular thing. This is actually the difference of two consecutive reciprocals. See, if you work out 1 over k, and that's larger than 1 over k plus 1, it's got a bigger denominator. If you subtract these two, you will get k plus 1 minus k. You'll get exactly this. So this quantity here, k squared plus k, is really 1 over k minus 1 over k plus 1, right? So I can replace all these things here accordingly. Let's get to the next sheet. I do have an open sheet here, notice. Let me just open that. So we need to work out a subscript m just give me a break. There's some, all right, let's take all these things out. But I want to use this fact here. I need to calculate a subscript m plus a m plus 1, a partial sum, m plus 2, going all the way up to, they choose n minus 1, right? And they say that this is equal to 1 over 29. So I'll put 1 over 29 this side. 1 over 29 is equal to all this. Okay, we'll just remember that rather than squeeze it in so unceremoniously in this thing. Just remember that the sum is 1 over 29. All right, so according to this AM, this AK. This is the kth term. So this will be AK is 1 over K minus 1 over K plus 1. So this is 1 over M minus 1 over M plus 1. Then you got plus 1 over M plus 1 minus 1 over M plus 2, and so on, until you come to this last one here, is 1 over N minus 1 plus 1 over N, right? And you'll notice that all the in-between terms cancel. A very popular trick. And this one here would have also cancelled with its neighbor. So in the end, you'll have 1 over M plus 1 over N. See? And this is now equal to 1 over 29. It's a very, very nice, beautiful problem where this rather complicated thing simplifies quite nicely to 1 over M plus 1 over N. All right. Now, the problem is, what is M plus N? So we're still not finished here. They did also say that M is greater than M can't be greater than N. Let's see, what do they say? M is less than N. I think they said M is less than N. It has to be because, okay. Okay, let's just see. These are whole numbers. When you simplify that, you get M plus N over M. If you cross multiply, you get M plus N is equal to 29 Mn. So, well, M plus N is some multiple of 29. But what is it? So now this is a challenge. At this point, most people will just get stuck. Because we got two unknowns, but one equation, and how are you going to solve? All right. So let me just create some space here. Bearing in mind, we need to calculate M plus N. So what I'm going to do is the following. Bring all to one side. Make it 29 Mn minus M minus N equals 0. Interestingly, you can proceed from this. I can take M out, and watch. I can take M out as a common factor here, and I will get 29 N no, this is wrong here. I'm sorry. When you cross multiply, you get 29 into M plus N is equal to Mn. All right, so cross multiplying, I'll get 29 into M plus N. So I'll put Mn minus 29M minus 29N equals 0. And when you take it to the other side. Now here you can take out your M as a common factor. and you're left with minus 29n. Now, this minus 29n, I'm going to put minus 29, and I'm going to force this to be a common factor. I'm going to put this. So now I've got n minus 29 is a common factor, so I can factorize this. But now I've done something here. I've got minus 29, and I've actually added 829 squared to both sides. Okay, so I've added 29 squared to 0. So I got 29 squared on this side. And now what happens is I've got n minus 29 into m There is a mistake here. You see, this last one was 1 over n minus 1 minus 1 over n. I shouldn't have had a plus here. Okay, so we're not infallible. Everybody makes mistakes. So sometimes when I am busy doing something here, it looks as if I can't make any mistakes at all. Instead of putting a minus sign, so this is supposed to be m minus n, all this m minus. So I got 29 m, this should have been plus here. And now you have plus 29. Yeah, I should have had plus 29 into n minus, and here I'm adding minus 29 squared to both sides. And you got n minus 29 into m plus 29. Okay, now at this stage here, it's still not easy to see what's going on here because you've got a factorization of a negative number. This thing has got lots of factors, right? And these are all integers. It was given that m and n are positive integers. Oh no, no, that wasn't given actually. Um, no, wait a minute. I think that was given. Let me just check. Yeah, positive integers. Can you see here? Positive integers. So m and n are both positive integers. So that should be able to help. So m is positive, and so it says that this particular factor m plus 29 in this. I just want to look at this. This is greater than 29. So this m plus 29 is a factor of this, which is greater than 29. Now, if you look at the square of 29 is a prime number, right? And if you look at all the factors of this, the factors of this are m plus 29 is a factor because if you multiply these two, you get this. The factors of this are plus or minus 1, plus or minus 29, plus or minus 29 squared. This is a prime number, you see, 29. So it's got no other. Now, which of these is greater than 29? Neither of these. This is exactly equal to 29. Neither of these. One of them is negative. So therefore, this is the only one. M plus 29 is actually equal to 29 squared. That's the only one which is greater than 29. Okay. And so that gives you can calculate M now. M is equal to 29 squared minus 29. That's 29 into 29 minus 1. Okay, you can work it out. I think this is 812. And if m plus 29 is 29 squared, so that means that n minus 29, this is n plus 29 is plus 29 squared. So n minus 29 will be negative 1. And therefore n will be plus 29 minus 1, which is 28. So there it is. You've got m is 812, n is 28. So m plus n is equal to 840. I'm sure there are easier ways of doing this. Like for instance, look at this. The two factors, when added, will give you m plus n. In other words, what is the sum of the two factors here? One of them is 29 squared, and the other is minus 1. So the question is, what is the sum of these two factors? And there it is. It's 29 squared, and you add negative 1 to that, and you get 29 squared minus 1, and there's the difference of two squares, 29 minus 1 to 29 plus 1. Lo and behold, you get 840. So I didn't have to do all these other things. See, mathematics with numbers, you can do it. You have to observe certain things and it'll help you a great deal. The problem was to work out m plus n. When you come to this, you say, hey, wait a minute, m plus n is just the sum of the two factors of this. One of the factors you can decide is 841, which is 29 squared, and the other is negative 1. Okay, so let's get on to the next problem. All right, you can see I've got the same answer. I'm not too sure whether I did it the same way, but that's it. Uh, I always give you these answers so that in case you missed something, you can get it out elsewhere. Now we are on problem number 23. There are 25 problems in this team, individuals. My own personal opinion is that there are far too many. I don't know how much of time they give you, but all of the problems are hard. So I think even if you get 7 out of 25, consider yourself very good, because they are hard problems, take a long time to work out. Now, in a trapezium ABCD with AB parallel to CD, the diagonals intersect at P. So let me draw that. You get a trapezium. So one pair of sides are parallel, but they're not equal. Um, the diagonals intersect at P. So let's just get these trapeziums named. You got A, B is parallel to CD. We always name it in a one direction. You can't put A, B and go C there. You have to keep going around in the clockwise or anti-clockwise direction if they name it like that. And they intersect at P. The lines are parallel. The area of ABP is 72, and the area of CDP is 50. So these two areas are given, and they say, what is the area of the whole trapezium? In other words, you want to know what is the sum of this and those two. You already got two of them. So the idea is to find these two. I want you to notice here, These two are actually equal. The reason is, if I take this area and add 72 to it, right, I will get this entire area here, ABD. And if I take this area and add the same number, 72 to it, I'll get ABC. But this triangle ABD and ABC are equal in area. You see, they are like, they got the same base and they lie between the same two parallel lines. Those other 2 points are on the other parallel line. So you'll always have, no matter which point you take here, all these triangles will have the same area. The reason being that they all got the same base and they got the same height because these are parallel lines, you see. So therefore, the point is that this plus 72 is equal to that plus 72. So these two areas are actually equal. Let's call that X. Right. Now, I suggest that you can actually calculate X. The reason being that when you have a triangle, take any triangle, and you draw from any vertex, you draw a line to the point of the other side. So you split the triangle into two pieces. Need not be equal. Any two pieces. It turns out that the ratio of the areas, this area over that area, if you could call it area A and B, and these are the side opposite the base side is A here. It turns out that the ratio of A over B, these two lengths here, is the same as the ratio of the areas, A over B. And that's very easy to see because they got the same height, you see. A and B have got the same height. So when you work out the area of A, it's half base times height, and this one here is half the other base times height. Those two things will cancel up, and you'll get this. You can check it out, right? So in this particular case, I have that if I take dP over PB, dP over PB, I get X over 72. If I'm looking at that triangle there, dP over PB is X over 72. But if I've changed the focus and I look at this triangle, then dP over PB, the same thing, is now equal to 50 over X. Right? It could be this area over that area, that the same ratio. Now you got 2. X squared is equal to 72 times 50. You don't need to multiply them. Well, you can. In this particular case, it's easy. So X is 60. So which means that this area that we are looking for is 60, 60. So the area of the trapezium equals 72 plus 50 plus 60 plus 60. That's 122 plus 120, which is 242. Square centimeters. See, the area, the units are given. Square centimeters. So that's the answer to this one. 242 is the answer to that problem. Um, there it is. You can see I had worked this thing out to be the same thing. Let's now go to question number 24. Hey, you got like a Batman face here. Anyway, well, I'm sure I'm not going to read all this. The whole picture is here. And obviously, you must calculate the total area of the shaded regions. So we need to calculate the shaded area. And you've got a small number of pieces here. Yeah. For one thing, I can see I've got a semicircle here, going all the way. And I've got another semicircle here, another semicircle here. Now join these lines and then shaded up these parts to get this. So I need to calculate the shaded area. They say CD is equal to 2 and AE is equal to DE. We don't know what they are. All right, AE is equal to DE. These are equal. Yeah, but I think we know what they are. Okay, if you join, if you take this point where these two semicircles meet, and if you draw the common tangent, it must go up here to that point, right? And so in this rectangle here, this is 2, so this will also be 2. All these sides are 2. But now you will see that E is the center of the circle, as you can see, because you can see this is it's a semicircle. This is a semicircle, and this is a diameter. So the midpoint of this is the center. And you can see the radius is going to be 2 from here up to that. So in fact, all these things are 2. They don't tell you it's 2, but you can deduce it because this is 2, that will be 2, but that is the radius. So you actually got two squares here, identical squares, right? And they are identical. The one is just a reflection of the other. You can see, right? So I need to actually calculate just this, the shaded part here on the left-hand side. Okay, so this is a very, very funny shape. Instead of calculating the shaded part, I think it might be easier to calculate the unshaded part. So let's call this unshaded part here X and Y and Z. Right. Now, you can see by symmetry, this is a square. And when you join the diagonal, right, it divides the square up into two equal parts. So therefore, you can see this part here will also be X, right, by symmetry. Right. Okay, that part is also X. And now another interesting thing here is that this is a diagonal of the square. And if you join the other diagonal, it looks as if the other diagonal is going through this point here. Okay. And in fact, it does. It's not very easy, but I'm sure those the students who try this problem, they wouldn't bother about trying to prove it. They will say, yeah, obviously this is the center of this. And they will say that all these 3 points are, these 3 lines meet. But the actual argument is that the square, the two diagonals intersect at right angles, always, in every square. So now this diameter subtends 90 degrees. So this point here must be on this semicircle. All the points whose angle 90 degrees, which A is subtends, all lie on the semicircle. So that point does lie on the semicircle. All right. Now, why did we have to do that? Because once I do this, you can see this part here is 2. So therefore, this part is also 2. Because now you got a symmetry. Oh, I'm sorry, this was Z. Can't even understand my own writing. So I need to calculate X plus Y plus Z. I want to calculate the white areas. Right. But now I've translated all these point areas to here. Look, X plus Y plus Z is just the area of this triangle. Amazing. See, X plus Y plus Z is the area of this triangle. And this triangle is just a quarter the area of the square. Because these two diagonals, you see, these are all properties of a square. The two diagonals, they divide the square up into 4 equal areas, 4 congruent triangles. These are very special triangles. They're right-angled isosceles triangles. Anyway, so this is the quarter the area of the whole square. The area of the square here is 2 squared. So X plus Y plus Z is 1. So the left shaded area I'm calling this the the area on the left hand side. All the shaded area here is 4, which is the area of the square, minus the white part. The white part we just calculated is 1. Right? So left shaded area is 3. And therefore, by symmetry, the right shaded area is also 3. So the answer is calculate the total area of all shaded regions. You have to say by symmetry that the areas on this side are replicated on this side. You can see it's all the same thing. So therefore, whatever you calculate for this will calculate for that. Here, the shaded part will be 3. So both shaded together will give you 6. Okay, so that's a rather tricky problem. And I've done it here again. So you can have a look at it. Oh, there it is. So you got the answer is 6. And I've done it almost identical to what I just told you. All right, so let's go on to, thankfully, this is the last question. Now, before I do this, I want to tell you something which I use very often, but it's not very well known. Um, Let me see whether I can get a, oops. Sorry. All right. So this was a question which I just lost temporarily. I thought I can try to get some extra space here. How do I do that? To this. Oh, come back to this thing. Oh God, I'm in trouble. All right. Okay. I can't seem to get the extra space. Okay, what I want to tell you is the following. You see, if you have any number and you ask the following question, given a number, say n, find all squares a and b such that n plus a squared is equal to b squared. Find a square number which when added to n gives you another square. See? Like I can tell you if you take 36, but it's a take any number. Take like uh, let's make it interesting. Make it 56. Right? Which square number must you add to 56 to get another square? I can tell you it's 190, 169, 13 squared. It's 56 plus 169. 69 is 15, 1 and 6, 7 and 5, 12, 225. And I think you should know that 225 is 15 squared. There it works. Okay. But you could have taken 25, 5 squared. Now 56 plus 25 is 81. That's 9 squared. So your question would be, you'll be asking, how did this guy get 13 and 5 so quickly? Right? And what I'm going to tell you now is the trick to get these numbers. Right? It's very easy. You'll have to do the following. You take the number at hand, like I got 56, right? You factorize it. But you factorize it so that both the factors have the same parity, which means that either both are even or both are odd. You can't have both odd here because if you multiply two odd numbers, you can't get to 56. But if you take both even, you can have 2 plus 2 times 28, or you could have had 4 times 14. Right? All you need is just a factorization. And the number that you're going to add to this to make it a perfect square is the difference between these two divided by 2. See? 28 minus 2 divided by 2. And that's 26 over 2. That's 13. You remember? We put 13 squared. Right? So you can take that, gives you 1. And the other one, if you take 14, the difference between the other factorization is 10 over 2, 5. And you remember I also told you 56 plus 5 squared. So all you have to do is to calculate all the possible factorizations of your given number so that both the numbers have the same parity. Both must be even or both must be odd. Right? And then you can actually calculate what must you add. What must you add to n? What square must you add to n to get another square? So this is quite very useful to even construct right angle triangles with integer sides, right? I'll leave that to you as an exercise so you can practice this thing. All right, now to get back to our problem here, you've got two different positive numbers, a and b, satisfy this equation here. And the question is solve this equation here. All right, our equation is the following: a squared minus b squared is equal to 2024 minus 2a. I'm going to rewrite this thing. I see a 2a here. So let's put the a's together. You got a squared plus 2a equals b squared plus 2024. Right. Now, this is quite a familiar friend because if I add 1 to it, I get a perfect square, you see. If I add 1 to this, it's a plus 1 all squared. And that is equal to b squared plus 2025. Now, this is exactly the problem that I was discussing now. Your number here is 2025. What square must you add to get another square? And the way to do that is to factorize this into all possible factorizations where they've got the same parity. Now, obviously, the two numbers will have to be odd because you can't have, you got 2025, I'm going to factorize it, right? So any factorization will do because both of them will have to be odd. So let's start with 1 times 2025. The next factor is 3. You have to try it on. You can use your, see, 5, you know 3 goes into it because 2 plus 2, the sum is 9, so even 9 if it goes to it. I'm going upwards from the smallest to the highest. 135 times 405, and that's 5. Let's come back to this. Let's see whether I can retrieve. Okay, I lost all that, but uh, I was at this place where I had a plus 1 all squared. I had something like this: b squared plus 2025 was equal to a square. And I said, all you have to do is to factorize. So they said, how many pairs? So the question is the same as how many b's? How many b's satisfy this equation? And I said that b, okay, first you have to factorize it. 2025 is 1 times 2025. I was busy with this before I got knocked out. 3 times 675, 5 times 405. I came to 9. 9 times 225. The next one is 9, 10, 11, 12. I think it's 15. 15 times 135. It's got a lot of factors, odd factors. And the next one after 15 will be 25 times 81. The one after this is 27. 27 times what? I think 27 times 75. Okay. So so your B will be any one of these. You subtract these two and divide by 2. So you get 2024 minus 1 is 2025 minus 1 is 2024, and divide by 2 and you get 1012. So that's one of them. And this one here will be, okay, I don't really have to find all of them. I need to know how many. 1, 2, 3, 4, 5, 6, 7. So there are 7 possible factorization of 2025 which have the same parity, and they will give you 7 such B's. You can try it out. You'll see it works. And those are the only ones. So the answer is 7. Okay, well, not many people will use this method here, but I find this a very powerful method. That the question, what square must you add to a given number to get another square? And this is the technique in doing it. Right, so let's just go to the actual solution that I give. Let's see if there's 7. Oh, yeah, okay. In fact, I explained everything, the same thing. There are 7 solutions. Okay, so that brings us to the end of the 2024 senior individual paper in the team competition. And I can safely say that it was a very hard competition. I think very few people would have got scored high marks in that because the questions were hard and they took a long time to work out. Okay, thank you and have enjoyed the rest of the day or the evening.